certain property hold. So do we start again? Or? Okay. Yeah, thank you very much for the nice introduction. Today I will cover Friedman style independence results. And I will speak about two principles, the slowly well-orderedness of ordinals and the combinatorial well-quasi-orderedness of the set of finite trees. The principle of the slowly well-orderedness is the following. We have a statement. For every k, there's a number m. M is so big that something holds. Namely, we know if you have a given infinite sequence of ordinals, it cannot be strictly descending. Now something similar holds now for sequences of length m plus 1. Namely, the conclusion will be that under certain conditions, there will be a number I less than m, such that alpha I is less than or equal to alpha I plus 1. Now, what does this conclusion mean? This conclusion means that this is not a strictly descending sequence. Now, of course, here comes a condition, and as it stands, the statement is now not yet complete. And the condition is a growth rate condition for all I less than or equal to m. The complexity of the ith ordinal, so the norm of it, is bounded by k plus I. So for every k, there's an m, such that for all sequences of length m plus 1, if the complexities of the ordinals involved are growing in a linear way, then there is an I below m, such that alpha I is less than or equal to alpha I plus 1. The corresponding statement for finite trees, Friedman's version of Kruskal's theorem, is the following statement. It looks very similar. For all k, there's number m. M will be a big number, such that for all finite trees, I will define later what these are. So we have a given finite sequence of finite trees. Again, if we have a growth rate condition on the finite trees, namely the number of nodes in the ith tree, denoted by this symbol, is bounded by k plus I. So if this holds, then now the conclusion is slightly different. Then there will be numbers I and j. Less than or equal to m, such that I is less than j. And the I is, in a certain sense, homomorphically embeddable into Tj. So this embeddability means that Ti can somehow be moved in a natural way into Tj. And what's the point here? These principles are true statements. This can be proved by an appeal either to the well-foundedness of the ordinals or by the well-quasi-orderedness of the set of finite trees. If time is left over, I might come back to this. But today I want to show first that these principles are not provable in pairs arithmetic. So the goal is to show PA does not prove the first principle, and PA, or the system Z, which we considered before, does not prove Friedman's version of Kruskal's theorem. Now, in doing so, I make certain simplifications. I don't prove the theorems as they are, but I start with discussing weaker versions. So I discuss a new principle, SWO prime, but it looks very similar. For all k, there's an m such that for all ordinals, alpha 0 to alpha m in E. If we have that for all I is less than or equal to m, the norm of alpha I is bounded by, and here I take k times 2 to the I plus 1 square. So the gross rate condition is a bit weaker than over there. Then there is an I less than m such that alpha I is less than or equal to alpha I plus 1. And we prove a similar version fkt, we consider a similar version fkt prime. It's this statement here, where I replace k plus I again by k times 2 to the I plus 1 square. And I show that those ones are unprovable. And further, I consider a statement H, which is the following one, namely for all k, there's a number m such that if I take a tower of omegas of height k, so omega k is omega to the omega to the k, height k. And then I start fundamental sequence at argument 0. And I take the result, take fundamental sequence at argument 1. Then I take this result, take fundamental sequence at argument 2. And finally, I take fundamental sequence at argument m. So this forms a descending sequence of ordinals. Of course, at some moment, it has to hit 0. But the waiting time until this happens is bounded by this number m. And that m will be rather big. Now, some comments. How big are these numbers in these principles? These numbers m as a function of k will be rather big. So if you want to win a game on a party, who is naming the biggest number? Normally the first player loses, because if he plays 3, the other one comes and says number 4. And so the first player is lost. Now, you write a number on the board, you say, a given number, let's say 100, it takes the corresponding least possible m. You put it in an envelope. Of course, you should not open it. And then you say, this is my move. You play as player 1. And then player 2 can choose a number. And then you are almost sure that you will win the game, because this number for fkt, so k equal 100, will almost sure be bigger than the number everybody can think of. These numbers are extremely large. Now, how to prove these results? So I will show this principle, SWO prime is unprovable, FKT prime is unprovable, and H is unprovable. Now we start with H, and this is somehow easy, because in our second lecture we have learned PA does not prove for every X there is a Y. H E of X is equal to Y. Now this can be reformulated, because E stands for epsilon 0. So H E of X is H omega tower of height X. So this means PA does not prove for all K. There's M such that H omega K of X, X is K, is equal to M. Now, for this principle, let's say Hardy, for the unprovability of the totality of the Hardy function. Now we want to show that assertion H is unprovable. So show H implies principal Hardy. Since Hardy is unprovable, assertion H is unprovable. Now, what is important? Important is, of course, to recall the definition of the Hardy functions. So what is the definition of the Hardy functions? H0 of x is x. And if alpha is different from 0, H alpha of x is H alpha, fundamental sequence at argument x, applied to x plus 1. Where it's assumed that if alpha is a successor, then alpha x is just cutting off the last one. Now we read what does H omega k of k, what is this? H omega k of k is the same as H omega k of k plus 1 by definition. This is the same as H omega k, argument k, of k plus 1. And here we get k plus 2. Now this continues. And at some moment, we find, well, these ordinals are decreasing. Find some number m such that if I add here an m, let's say here is m minus 1, here is k plus m. At some moment, this number hits 0, and h0 of x is x, so this is k plus m. So what is the upshot? This Hardy function measures how long it takes to step down from ordinal omega index k, starting with k, until we hit 0. So the least m such that omega k of k until we hit m, this is 0, is basically as good as the Hardy function. Well, there's small difference, starting value small k, but we do not bother too much about this. Now what is going on here? Here we start with omega k and step down. Now we want to prove that H implies Hardy. That's not exactly the same, because in Hardy we start here with k and finally hit 0. Here we start with 0. Now that's not such a big problem. So assume assertion H. Let k be given. And now I apply assertion H, not to k, but to k plus k. Apply H to k plus k. Okay, then H says for this number, then there is by H, a number M such that we start with omega k plus k. Here we have 0, 1, and here we have M. Now, why I take here k plus k? Because if we do here the first k moves, then we are sure that we end up with a number which is bigger than the number omega index k. And now it's some sort of technical verification. So this number M is bigger than the least, well, it's bigger than H omega k of k. It's bigger than the least number such that if I start my stepping down at position k. Now to do the verification, one needs to work a bit with ordinals. It's technical material, but it's not really difficult. So how to prove that this number M is bigger? For this one has to introduce specific properties of our ordinal system and our fundamental sequence. So the point is the situation, you have the so-called, what is called Bachmann property. And the Bachmann property is the one which is crucial for our system of fundamental sequences. So what does this say? If you have an alpha x smaller than beta, smaller than alpha, then now it depends a bit on how the fundamental sequences are organized. In our context, we have alpha x is less than or equal to beta of 1. So this means the fundamental sequences are somehow nested nicely together. So if I'm in this interval between alpha x and alpha, if some beta, and I step down in the fundamental sequence, I can be sure whatever I do, I will finally hit alpha x. Because beta 1 is of course bounded by upper bound is beta of y for all y at least as big as 1. So whatever I'm doing here with the beta, at some moment I will hit this number. We say alpha is less than 1 beta if and only if we step down from beta to alpha just using stepping down with respect to 1. So this means alpha can be gotten from beta by stepping down at fundamental sequence 1. Another one. So there will be finitely many stepping downs. There will be some finite number r which is bigger than 0. That's this stepping down relation. The stepping down relation has certain closure properties. So what are the closure properties? If I can step down from beta to alpha, then I can step down from gamma plus beta to gamma plus alpha. So if, now it's important, this does not work for all ordinals. So if gamma has certain normal form, omega to the gamma 1 plus omega to the gamma m, the exponents are weakly decreasing. And alpha is the same description. and alpha 1 is at least as big as alpha n. And if what? Gamma m is at least as big as alpha 1, then we have that gamma plus alpha is reachable from gamma plus beta. Now, this technical extra condition has to do with the effect that there are certain underlying ordinal operations involved. And if one works with the normal forms, then everything behaves properly. So the point is, I want to have at all these stepping downs that property like that the fundamental sequence of gamma plus beta of x is the same as gamma plus, then it takes the fundamental sequence for beta. Similarly, one can verify, that's part 1. And part 2 is closure under exponentiation. So if we can step down from beta to alpha, then we can step down from omega to the alpha, from omega to the beta to omega to the alpha, also along stepping down along 1. Now the stepping down relation has certain properties, namely if alpha is less than x beta and x is less than or equal to y, then alpha also steps down, and beta steps down to alpha, also for beta indices y. These are the crucial properties for our system of fundamental sequences. And then one can just check if one starts here with this number. There will be a finite amount of time where we hit omega k of k. Then, after stepping down at least one step, we can find out that in this sequence, after some time, we will see omega k, k plus 1, etc. So all the elements which are showing up here are showing up also in this sequence only at some postponed moments. And that basically shows the claim. I will not go too much into details, but this is basically what the verification gives. So that proves the first of the independence results for today, namely this principle H is not provable, unprovable in PA. And actually this principle H has to do with the famous combinatorial principle, namely the unprovability of the winning of Hercules in the Hydra game against the Hydra. So this formulation of a classical story from Greek mythology that Hercules had to fight against a dangerous snake with many heads. And there's a mathematical formulation by Paris and Kirby. And this has to do with this property. And H is a resulting mathematical assertion, which has to do with the termination of the Hydra battle. And now we have seen the termination of the Hydra battle is not provable in PA. So maybe at some time is left, I could also explain the relation between this statement and the modeling of the Hydra game or the Hydra battle. But I will now move on to discuss the two other principles which are over here. And for this, I will clean the board. Okay, so now we want to prove the first principle over here. And what we will show is principle SWO implies principle H. Aha. Well, for this, we have to recall what is H. For every K, there's M such that we start with omega K, take a 0, 1, finally we get M, this is equal to 0. Now, let alpha 0 be equal to omega K, and alpha I plus 1 is, I take alpha I at argument I. So, what can I say about the norm of alpha I? Well, technical lemma. If I want to calculate the norm of alpha I, well, basically it's a function in the norm of alpha and I. Now, we take, for example, norm alpha times I plus 1. This is an upper bound. This is sort of easy calculation to verify this. And the norm of omega K will be, by our definition, K plus 1. Now, what was the norm function? The norm function was defined as follows. The norm of 0 was 0, and the norm of omega to the alpha plus beta was 1 plus the norm of alpha plus the norm of beta. And then it's easy to verify these properties. So what is important here? What is the norm of omega? Omega is a form omega to the 1, which is omega to the omega to the 0. And therefore, the norm of omega is 2. And therefore, the norm of an omega power of height k is k plus 1. Okay. Now we prove principle H. So assume principle SWO prime. Let K be given. I have to find number n, one upper bound for this. Yeah. Now apply this principle SWO prime to number K plus 1. So for K plus 1, I will find a number n. Find the corresponding number n. And then we have, if we have a sequence with this growth condition, then the sequence is not quickly decreasing. Now, what can we say about the norm of alpha I? Well, we have this lemma. The norm of alpha I is what? It's the norm of alpha I minus 1. Well, maybe I take here alpha plus 1, I plus 1. Then it's the norm of alpha I of I, which is bounded by the norm of alpha I times I plus 1. Now you see, one can sort of do induction. So this will be bounded by the norm of alpha 0 times 1 times 2 times I plus 1. Aha. Now, alpha 0 is omega k. And the norm is here k plus 1. So this will be bounded by k plus 1 times I plus 1 factorial. So this will be bounded by 2 to the I plus 1 square. Now you see why I come up with these specific bounds, just to make my life happy, easy. Just obvious bound, which I plug in here. And tomorrow I will indicate how to make this bound smaller. But for today, it's fine. So we have found a sequence fulfilling this condition. Then by the principle, we have that there will be an I less than M, such that alpha I plus 1, that alpha I is less than or equal to alpha I plus 1. Now, if alpha I is different from 0, then alpha I plus 1 will be smaller than alpha I. So this means alpha I has to be equal to 0. So what does this mean? If we have found an M, then we found an I less than or equal to M, such that this sequence hits 0. Therefore, we have shown that H is true. So H is shown. So you see, today I just provide some easy proofs. And what is the philosophy here? The philosophy is we have one big result. It's the unprovability of the totality of the Heidi function. And then we apply this and get some other result out of it. We have proved the principle H. And now we have seen that if we have SWO prime, we can prove H, and H proves the Heidi principle. So therefore, SWO is unprovable. Okay, so first goal achieved. This principle is unprovable. Now we want to see the second one. Why is FKT unprovable? Well, it's just the same. We show now that FKT prime implies H over a weak theory. Now this is not so clear yet, but before continuing, I will explain what are the finite trees. There are different ways to define finite trees. So what are finite trees? Well, one has to be careful. There are so many definitions of finite trees. One just has to be, one has to make clear what version one is using. And I'm using here a version what is called non-planar trees. And I write them on the board. So what are the trees? Well, tree consisting of a root is a tree. And if, so it's an inductive definition. If I have a sequence of finite trees, then I form a new tree, namely a root, and then I connect the root to the immediate subtrees. So graphically, one would visualize this as follows. One has here tree T1. Here's tree En, and here comes the root. And this is just a sort of other way of representing this graphical notion. Now it's important to say what is meant by tree embeddability. And there are also different versions. And I use the one for non-planar trees. So assume, so definition, tree embeddability. So assume that tree T is a form that has a root and some immediate subtrees. It could also be that the number n is equal to 0. Anyway, if tree S is a singleton tree, then of course I want to have that S is embeddable into T. So a tree just consisting of a root sits in every tree. That's fine. Now if S, this definition of this embeddability relation is also done by recursion. If S is embeddable into one of those immediate subtrees, then S is embeddable into the whole tree T. That's also fine. And now we use the version of non-planarity. If we have a function h from the set of indices, if S is a representation, a root, and then some immediate subtrees, and if H from the set of indices 1 to m of the tree S goes 1 to 1 into the indices 1 to n over here. Now there are two versions. One is that H is strictly increasing. The other one is just 1 to 1. And these two differences are measured in the difference between planar and non-planar trees. Either definition is fine for us. We now use just here injective mapping. So if this is going to happen, and for all L less than or equal to M, we have that S L is embeddable into T H of L. Then S is embeddable into T. Now, one has to be careful. So I define an equivalence relation. S is equivalent to T if S is embeddable into T and T is embeddable into S. And if I identifies trees which are equivalent, then one has a class of non-planar trees. If one does not like this type of identification, then one could also use here, instead of this notion, strictly increasing function. That would be a variant of Kruskal's theorem, which is also fine. It's also leading to an unprobability result. Anyway, this is the definition. Now what? Define now a transition function T from ordinals into trees. So what is this? Well, the tree belonging to ordinal 0 is given by singleton tree just consisting of a root. And if I have ordinal in normal form, tree associated with this ordinal in normal form, actually, it does not matter whether it's in normal form or not, but I assume it's here for having a good definition. The tree associated to this ordinal is what? I take just the trees for the subcomponents. So this is a list of finite trees, and I connect them with one root. So this moves all elements of E into the set of finite trees. Actually, this is a nice mapping. So this is a sort of bijection. So every tree can be identified with an ordinal in E and vice versa. Moreover, what can be said about the number of nodes in T alpha? This is 1 plus the norm of alpha. That's an important observation, because it gives a transition between complexity measures. And note, for fkt prime, we work with the number of nodes, and here we work with the norm function. So this lemma basically explains how trees are connected to ordinals, and this tree association behaves also natural with respect to complexity measures. Now, this property is easily proved by induction. So if alpha is 0, T of 0 is just the singleton point. So the number of nodes in T0 is the number of nodes in singleton tree, which is 1. And this is 1 plus the norm of 0. But that's easy. Moreover, now let's look at this situation. What can we say about the number of nodes in T omega to the alpha 1 plus omega to the alpha n? Well, we use this description. So it will be 1 plus the number of nodes in this tree plus the number of nodes in this tree. So this will be 1 plus the number of nodes in T alpha 1 plus 1 plus the norm of number of nodes in T alpha n. All right. No. This is correct, right? So the number of nodes here is 1 for the root, the number of nodes in T alpha 1, and the number of nodes in T alpha n. Okay. Now we apply our induction hypothesis for the subterms. So we get 1 plus the norm of alpha 1 plus 1 plus the norm of alpha n. Now, if you look carefully, using the definition of the norm function, you see norm of omega to the alpha is 1 plus the norm of alpha. So this now distributes over the whole sum here. So this is the norm of omega to the alpha 1. So in total, this gives 1 plus the norm of alpha. Okay, that was easy. Now, what we can do is we can show FKT prime proves SWO prime. This is unprovable, therefore this is unprovable. So how does this go? So we want to prove SWO prime. So we start here with number k. I'm looking for a bound for this number m. Well, apply FKT prime to number k plus 1 and find number m. Number m for FKT prime. Number m has this property. And now I want to show that the number m for k plus 1 is good as the number m for this k in this principle. So I start with let alpha 0 to alpha m be given. Now I want to apply my principle. Therefore, I move the sequence of ordinals into a sequence of trees. Consider, well, let's use the number, this is sequence of ordinals, and assume that the ordinal satisfies this condition, such that the norm of alpha I bounded by k times 2 to the I plus 1 squared for all I. Now I want to find this I. I have no idea where to find it. The only thing what I know is I have a corresponding result for trees. Therefore, consider the corresponding sequence of finite trees. Now, okay, we have finite trees. What can we say about the complexities of the involved trees? The number of nodes in T alpha I is bounded by, now I use this law here. T alpha I is 1 plus the norm of alpha I. So it's bounded by 1 plus k times 2 to the I plus 1 square. Because I have this. And this is bounded by k plus 1 times 2 to the I plus 1 square. So it's a very rough bound. Now I apply FKT prime to k plus 1 I have the number of nodes in Ti is bounded by k plus 1 times 2 to the I plus 1 square. Therefore, by f by t, find I less than j, such that T alpha I is embeddable into T alpha j. So not much is going to happen. We just show an easy transition. Now comes the crucial property of this association of trees and ordinals. And I fix this in a lemma. The lemma is as follows. If T alpha is embeddable into T beta, then alpha is less than or equal to beta. So proof. Proof is by induction on the complexities of the ordinals involved. So of course, if alpha is 0, 0 is less than or equal, then we are done. Now if alpha is not 0, then alpha has a Cantor normal form. Let's say of this form. Then of course, beta cannot be 0, because if beta is 0, then here's a singleton tree. Here's a tree with more than one node. So beta is also the form omega to the beta 1 plus omega to the beta n. Now, what do we know? There are two cases. So this tree is embeddable into this tree. The first case is T alpha is embeddable. And T beta is now consisting of a root connecting the immediate subtrees. It could be that T alpha is embeddable into an immediate subtree. Then induction hypothesis would give alpha is less than or equal to this beta I. And now, if you look at the definition of this function class E, representing the ordinals, it is clear that every function f fulfills f is less than or equal to identity to the f. So this is, of course, less than or equal to beta. So we have shown what is over here. The second case is, well, T alpha has a form omega to the alpha 1 plus omega to the alpha m. No. The alpha is a form, so alpha is a form omega to the alpha 1 plus omega to the alpha m. And T alpha is a form, you have a root and the immediate subtrees T alpha 1 up to T alpha m. Now, the first condition is not satisfied, but we know that T alpha is embeddable into T beta. So there exists a function h from the set of indices of T alpha. This is 1 to m, 1 to 1 into set of indices from 1 to n, such that T alpha L is embeddable into T beta H of L for all L less than or equal to M. Induction hypothesis gives what? Alpha L is less than or equal to beta H of L for all L less than or equal to M. So here is alpha and here is beta. And for every exponent here, I find an exponent here which dominates this exponent. So this means finally that alpha is less than or equal to beta, just by standard monotonicity properties. Okay. Now we are going back to our proof. We found these numbers below M, such that T alpha I is embeddable into T alpha J. What does this mean? This means alpha I is less than or equal to alpha J. So what does this mean? This means the following. We started with sequence ordinals. And this condition here says one ordinal at time I is less than or equal to an ordinal at time J. So this sequence is not strictly decreasing. So this means the sequence alpha 0 to alpha M is not strictly decreasing. Now, if an ordinal sequence is not strictly decreasing, this means there will be an I less than M, such that alpha I is less than or equal to alpha I plus 1 by the linearity of the ordinals. Okay, now we have found this I, and we are done. Okay, maybe it's good now to make a break of 5 minutes. And what is going to happen after the break? I will start discussing what is called the Gaussian principle. This will be a new principle. It's not really an independence result by Friedman, but it is one of the most famous independence results for arithmetic. It's also easygoing. So you have seen today, the presentation is easy to follow. You have certain principles. You just prove one implies the other. And the proof is just, you take what you have, make some small modifications, and then the result is going to happen. The whole lecture is based on what we have seen in the second lecture, namely the unprobability of the totality of the Hardy function of level epsilon 0. And the rest is just reducing everything to what we have achieved in lecture 2. Of course, what is left to be done is moving these conditions into K plus I. You have to remove a product by a sum, but that's not so difficult because if you have a product A times B, that is easily shown to be bounded by A squared plus B squared. So moving products into sum is easy by moving up the numbers a bit. And then there must be a procedure moving sums into things of lower complexity. But this is, well, this we will see tomorrow. Okay, now we make a break of 5 minutes. And the presentation today will continue in this mode of presentation. Everything should be easy. The treatment of the Gaussian sequences is also relatively easy. The only difficult part is what we have obtained in lecture 2, namely the unprobability of the totality of the Hardy function. Okay, 5 minutes break. Okay, let us continue. So what is what have you seen in the first lecture is independence results by Friedman. And let me first make a historical addition, namely this one here, KT, is a classical version of Kruskal's theorem. And we have seen Friedman's miniaturization. And these principles are not only independent of arithmetic, they are also independent of stronger systems, namely arithmetical transfinite recursion, which is one of the big 5 systems in reverse mathematics. So Friedman is famous for these 2 independence results. How to prove those ones? Basically by the same methods, but you have to show then that a Hardy function index by ordinals less than gamma 0 is not provable in arithmetical transfinite recursion. This would require a different treatment, which would be too complicated to cover in this course. But once you have the classification of the provably recursive functions, you have nice independence results. Now, we can forget about this. We start a new chapter. So if you get lost in the first lecture, it doesn't matter. Now comes the second part, which is basically independent of the first lecture today. We are covering good sequences. And this is interesting because it's one of the most elementary independence results which exist for piano arithmetic. So we fix a number k, at least as big as 2. And then we develop natural numbers, positive integers, into normal forms. Now, the number 0 is a normal form by itself. Now assume that m is different from 0. Then we write m as k to the r times p plus q, where certain conditions hold, namely we sandwich m between k to the r and k to the r plus 1. Now we assume that p is smaller than k and q smaller than k to the r. With these side conditions, this is a unique representation, and we write this as k normal form. Well, why this is interesting? Because if you have a normal form, we can do something with this, a certain transformation. And the transformation is called base change. Now I use notation. So assume that m is a normal form, k to the r times p plus q, k normal form. Then the base change for m is defined as follows. mk is, and now base change means I replace the base k here by k plus 1. And I do base change recursively in the exponent. P is smaller than k, there's nothing to change. And I do base change in q. So what does this mean? Well, for example, if I have 2 to the 2 and I do base change in 2, this means I replace base 2 by 3 and I get 3 to the 3. Now, having defined base change, I can define a sequence. So start with m, and then say m0 is m, and m l plus 1 is given by take number ml. But if ml is not yet 0, and do base change. Now, base change requires that numbers are at least as big as 2. So here I start the base change with L plus 2, just in case that L is equal to 0. And then we subtract the 1. So the first player makes the number bigger, the second one makes the number smaller, and then we have 0. Now let's consider an example. Let's assume that m is 2 to the 2 plus 2. This is m0. What is m1? m1 is we replace base 2 by 3 and then subtract the 1, which is 3 to the 3 plus 2. Now what is m2? m2 is we replace base 3 by 4. Here is nothing to change because this is 2. We subtract the 1, it's plus 1. m3 is 5 to the 5. And so the numbers become bigger and bigger. And then you could, in principle, implement this as a program on your laptop. And you make a test. You give a number 10, and then you calculate is this a converging sequence or diverging sequence? And the computer will tell you this is divergent. Now, therefore, it's interesting. We write down the statement G. G is a statement for all M. There exists an L such that ML hits 0. Aha. Now, this is interesting. This looks like a wrong statement. And theorem is what? Theorem is first, G is true. So it's not a wrong statement, it's a true statement. That's already surprising. And this is what Principal Goodstein showed in his article in 1949. And later, Kirby and Paris showed that PA does not prove assertion G. And today we are showing both assertions. Now, the speculation is whether Goodstein was already conjecturing that this principle is independent of arithmetic. There is some historical discussion about this, but I'm unable to make serious comments here. But it could be that Goodstein was on the way of having the first independence result for arithmetic. But in his JSL publication, you will not find much about this. Okay. Now we need some theory. First lemma. But this is easy. If m is smaller than n, then after base change, mk is smaller than n after base change. Now this is not so surprising. Well, if m is smaller than n, then there is a reason why m is smaller than n. This means some coefficients in m are bounded by some coefficients in n. Then one applies induction hypothesis to the coefficients. And then by the same argument, you can see that mk is smaller than nk. The second observation is using this property. You can show if m is in k normal form equal to k to the r times p plus q, then after base change, we get a k+1 normal form. It's a form k+1 to the r, where the base change is carried out, times p plus q, where the base change is carried out. So preservation of normal form after base change is a crucial property. Now, this is also easy to show, because if M fulfills this property, it fulfills this type of inequations. Now, by the first assertion, inequations are moved into isomorphic inequations. And the isomorphic inequations show that after base change, you again have a normal form. This is an easy verification which you can do in your first year bachelor education. So there's nothing special about this, but this is just an important property. Now, we want to prove that this principle is true. Now, there is no easy way to do so. Discrete mathematics will not be enough. Because if discrete mathematics would be enough, you could formalize the argument in the Peano axioms. And we will show that this is not possible. So we have to use a trick. And the trick is we have to move numbers into transfinite numbers. And this is the same trick as we did in lecture 2. We had the proof system for number theory Z. And we moved the finitary system into an infinitary system. And then everything became easy. And we got the result on the provably recursive functions. The same thing is going to happen here. So what is a canonical way of making an ordinal, to associate an ordinal to a k-normal form? Well, I define CK, mapping of natural numbers into ordinals in the system E. So pk of 0, k, not so spectacular, will become 0. Now assume M is the normal form, k normal form, k to the r times p plus q. Then ck of M will be what? Omega to ck of r times p plus ck of q. So what is this? This is just the operation. Take your k normal form, replace every occurrence of k by omega, so it becomes bigger. Now the same argument which we used here, that m smaller than n implies stability of the inequation under base change, it also holds for base change replacing k by omega. So the lemma is if m smaller than n, then ck of m is smaller than ck of n. That is also easy to prove. Well, you take your number m, write it in normal form. You take your number n, writing it in normal form, and then you make case distinction. Yeah, but maybe it's better not to be too detailed. Basically, you cannot fail in proving so. Just take m in this normal form, n in this normal form, and then there are 3 cases, namely either the first part is the same in 2 numbers and q is smaller than the other q. Then you apply induction hypothesis on q. Then you assume that q is equal to 0. Then you check for p, whether there's a difference in p. Then just verify it. Or p is equal to 1, and then you apply induction hypothesis to the exponent. So I assume that this is working out. The second is a sort of transitivity. Namely, if one has m and replace base k by k plus 1. And then replaces k plus 1 by omega. It's the same as just moving k directly into omega. This looks like a trivial observation, but it's not trivial, because this only works if we have assertion 2 in this lemma here, because first we move m into k plus 1 normal form, which has the same shape. And then we can replace k plus 1 by omega, and then this is an easy verification. But it is really heavily depending on this property 2. But when property 2 here is achieved, then it's also easily achieved over here. Now what is the point? Now we have all the preparations done. And now we define a mapping O of M and L. So M is the starting value of our Goodsin sequence, and L has to do with the process. And that will be psi L plus 2 of number M index L. So what is going on? The theorem is basically if ML is not 0, then O of M L plus 1 is smaller than O of M L. Now, this theorem here proves the theorem over here. Because if all ML would be different from 0, then here we would be able to find a transfinite descending sequence of ordinals, which is not possible. So if all ML are different from 0, then you see here in L plus 1, I get a descent, and this cannot going on forever. Now the proof is easy. It fits on the remaining part of the board. So just look at this. So O of M L plus 1 is what? It's psi L plus 3 of M L plus 1. That's just the definition of the number. Now we go into the definition of ML plus 1. We assume that ML is not 0. Therefore, we have to apply this definition. So this is what? Psi L plus 3 if ML. I do the base change, replacing L plus 2 by L plus 3 and subtract the 1. Now I'm using the property 1 of this lemma. This number is smaller than the number M L L plus 2, where I don't subtract the 1. And then I can apply psi L plus 3 to this number. So this number here is smaller than this number. Therefore, psi L plus 3 of this number is smaller than this number. And look, here we first pick ML. Then we move L plus 2 into L plus 3. and then L plus 3 into omega by the lemma 2 over here. This is the same as psi L plus 2 ml, which is O of ml. Voila. It's a very nice condensed proof, depending a bit on these extra lemmata, but here's the heart of the matter, namely the conclusion. And in the standard model, you have that assertion G is true. So we have a true statement. Now we want to prove that this statement is independent. How is this possible? Well, this is difficult to prove because we have just a principle about natural numbers, and the independence results depend on, let's say, length of the descending sequences of ordinals. But the proof just uses the function psi k over here. They move numbers into ordinals, and the idea is that the elements of a Gaussian sequence relate to stepping down in the fundamental sequences in the principle H, which we have seen before. So I will just now clean the board. Or maybe I first continue over here. So for proving independence, we need the following result. Namely, C k plus 1 of mk minus 1 is bigger than ck of m, fundamental sequence taken at argument k. And now the left-hand side is smaller than ck plus 1 m of k, which is equal to ck of m. So this is already what we know from the material which we have. So we have to concentrate on this side. Now here you see basically what's going on. Namely, what you see here is basically if m is ml, then here is ml plus 1. So we squeeze these ordinals into the system of fundamental sequences stepping down. And in the Gaussian sequences, we start with m0, then m1, m2. And these numbers become bigger and bigger and bigger. And then you see the numbers here become bigger and bigger and bigger. And therefore, this relates to the Hardy principle, or this principle H, which we have seen before. Okay. Now, since this is so important, I would like to give at least a bit of a proof of it. So maybe some cases. So we write m as q to the r times p plus q. And we prove this property by induction on the complexity of m, or by induction on m. So there are certain cases. For example, the first case is q is bigger than 0. Now, what is m k minus 1? It is k plus 1. And then here r of k times p plus q. of k minus 1. Right? Q of k comes from m of k, and the minus 1 is this minus 1. Okay, now what is c k plus 1 of m of k minus 1? It is, this comes in omega. Here is ck plus 1 of r of k times p plus c k plus 1 of q of k minus 1. Now for this term here, I use this property here to see that this is omega ck of r. And to this, I apply my induction hypothesis. So this is c k of q, fundamental sequence at argument k. And no one has to recognize that this number here has a property that the exponent here, the exponents shown up here, are never bigger than this exponent. So the upshot here is that this is the same as, so you see, induction hypothesis gives brackets over here, the same as omega ck of r plus ck of q over here. And now we have brackets over here. And this is ck of m. So you see, it follows by an easy verification. There's no surprise waiting. The next case is that q is equal to 0. Then m is q to the k to the r times p, and there are subcases. The first subcase is p is bigger than 1. And the last case is p is equal to 1. Now what is going to happen when p is bigger than 1? I have to calculate what is mk minus 1. So it's what? It's this number, k plus 1 to the r of k times p. This is q of k is 0. So let's subtract the 1 this term. Now this is the same as q plus 1 to the r of k times p minus 1 plus q plus 1 to the r of k minus 1. And now this number here is k to the r is smaller than k to the r times p. So here I can apply my induction hypothesis. So c k plus 1 of m k minus 1 is what? I take here omega, and then I do the same trick as before. I replace ck plus 1 r of k by ck of r times p minus 1 plus, and induction hypothesis here gives ck of k to the r at not good. Via round brackets. And here come square bracket k. If I apply induction hypothesis to this term, I get this term. And then by the same argument as here, this is the same as ck k to the r times p at argument k. So also this case is just following by induction hypothesis. Now comes the last case, and I will put it over here. So it will not become longer. So the last case is 2.2. P is equal to 1. Now, in this case, M is k to the r. Now, this is a bit tricky because now the argument becomes a bit messy. So we have what? C k plus 1 m of k minus 1. Now, this is C k plus 1. M of k is k plus 1 r of k minus 1. Now we have this law for calculating a to the b minus 1, and that's the geometric sum. Now you see terms become messy, but I just take the first term in the geometric sum. So this is c k, and then I take here k plus 1. R of k minus 1 times number k. Now, what is this? This is by induction hypothesis. You have omega, and then I have ck r of k minus 1. So you have here ck r fundamental sequence applied to k. So that's important. So is ck plus 1. So this k plus 1 moves into omega. And then ck plus 1 is applied to this difference. This difference is this form. So I can apply, but I'm claiming here is less than equal to 2. Up to now, I think could be fine. So ck plus 1 of this one is at least as big as this one. Now, what can we say about ck m? Fundamental sequence evaluated at k. I want to show this number here has to be less than or equal to this number here. Now, this is what? M is k to the r. So it will be omega to ck of r evaluated at fundamental sequence k. Now there are two cases. It could be that ck of r is a limit. Then the fundamental sequence for this one is omega to psi k of r, where I apply k. So then omega to this term times k is at least as big as omega to this number times 1, which is the same as this one. Or, second case, this is a successor number. Now you have to remember the fundamental sequence for omega to the alpha plus 1 at argument k is omega to the alpha times k. If we have here a successor, then we have to subtract the 1 over here, which is given by this term, because alpha plus 1 at argument k is alpha. So here is, if this is alpha plus 1, then this is alpha, and this times k is the right one which is needed. So this term here is at least as big as this term. Okay, we have proved this lemma. That was a technical verification, but there's a sort of reason for this, because this is crucial for proving independence. Now we forget about this lemma. So basically, what we want to show now is from principle G, we obtain principle H. Well, how is this possible? So we have to show that we start with omega k, and then we step down in the fundamental sequence. So let k be given. Now, m of k, or let m be defined as what? A tower of exponentials of base 2 of height k. So when I have given my number k, I write down this number m, and now I apply Goodstein for this number m. So this will become my number m0. Now look at the following numbers. O of mi, which is psi I plus 2 applied to mi. Now we look at them step by step. So what is O of m0? This is psi 2 of m0. So we replace here base 2 by omega. This is an omega k, which is omega index k. That's already a good start for our Hardy principle. Now, what is OM1? It is psi 3 of M1. Which is psi 3 of M 0 where I replace base 2 by base 3 and subtract the 1. Well, now comes the reason why I have this lemma. This is bigger than psi 2 of m at argument 2. So this is omega k of 2. Now we calculate further. What is O of m2? This is psi 4 of m2, which is psi 4 of m1. So m2 is m1, where I replace base 3 by base 4 and subtract the 1. This is bigger than psi 3 of m1 applied to number 3. Now psi 3 of m1 is bigger than this one. Now, one has to be careful, because if alpha is bigger than beta, then it's not clear that alpha 3 is bigger than beta 3. The trick is that here we are in a situation where we squeeze in a number into an ordinal and stepping down in the fundamental sequence. So this means we can use our majorization relation with respect to the Bachmann property. And then this here is a valid step. Well, I will not go too much into details, but one can verify that this is true when it's this property. So one gets here stepping down the fundamental sequence. And now you can judge how it continues. This one here will be bigger than omega k 2, 3, and 4. So O of ml will be bigger than omega k 2, 3, until we hit L. And then the principle that for every k, there will be an L such that this number hits 0. This is unprovable. Now we see the Gaussian sequence give rise to a descending sequence of this form. If Gaussian principle is true, then all these stepping down sequences will terminate. And so the least L such that ML is 0 is at least as big as the least L such that omega k 2, 3, etc. It's 0. And we know that the last assertion is describing a variant of the Hardy function. And the totality of the Hardy function is not provable in pair-arithmetic. Therefore, G is not provable in pair-arithmetic. Okay, that is the treatment of the Gaussian principle. Now, what is waiting for tomorrow? Tomorrow I will cover things like this. We have seen today principle H. stating for all k, there is m such that omega k start with 0. Finally, I find an m such that I hit 0. We can consider the corresponding assertion H index F, where F is a function from natural numbers to natural numbers, and assume for simplicity that is basically a monotone function. Yeah, we assume that is monotone, let's say. Then we replace here 0 by f of 0, and we step down along f of 1. And so we wait until we step down along f of m. And the question is, for which functions f is the function, is the assertion hf independent of arithmetic? And it turns out if f is a fixed iterate of a log function, then PA is unable to prove HF. And if f is the inverse of the Tower function, then PA does prove HF. And that is an example for a phase transition. And a phase transition is also possible for Friedman's miniaturization of Kruskal's theorem. So here I will go to the bound k plus r times binary log of I. This is then correspondingly rounded. And I will show there's a critical constant C. There is C. Such that if R is less than or equal to C, PA does prove FKT. Well, this is, let's say, bounding function FR. FKT for bounding function FR. And if R is bigger than C, then PA does not prove it. And I will give the precise value. C is 0.63, and then so there's an explicit description in terms of tree constant related to the enumeration of finite trees. And this C is what? C will become 1 divided by binary log of alpha, where alpha is coming from the asymptotics of binary trees, arbitrary trees. The Tn is the number of trees T, such that T has n nodes. And this has an asymptotic law, an exponential law, and this is basically asymptotically equal to alpha to the n times the constant divided by n 3/2. This number alpha is, the nature is unknown, could be a transcendental number. And this number C is well a primitive recursive number. So one can speak in pianostic about this number. And this alpha, we take 1 divided by binary log of alpha. And this again gives a sharp phase transition for Friedman's miniaturization of Kruskal's theorem. Okay, this is all what I want to tell today. Thank you for your attention.